Imagine you are standing in your room, holding your phone, wearing your favorite hoodie, or looking at the computer screen in front of you. Nearly every single piece of that reality took a journey before it reached you. It didn't fly on a plane because air freight is far too expensive for bulk goods. Instead, it sat inside a steel box, stacked 20 stories high, on a vessel longer than a skyscraper is tall, plowing through the middle of an unforgiving, pitch-black ocean. If you've ever watched videos of these giant cargo ships crossing the sea, you've probably seen footage that looks like a special effect from a Hollywood disaster movie. You see towering slate-gray waves that crest higher than the ship's bridge. You see hurricane-force winds tearing spray off the water and reducing visibility to zero. There are walls of water thousands of tons heavy crashing directly over the bow, burying the deck in foam. Entire ships completely disappear behind a mountain of water, only to stubbornly climb back into view moments later. It looks like madness, and it looks like they are seconds away from plunging to the bottom of the ocean. Yet every single day, roughly 50,000 merchant ships are out there, navigating the roughest patches of water on Earth, from the North Atlantic winter storms to the notorious roaring 40s of the Southern Ocean and the unpredictable typhoons of the Pacific. How do these floating steel islands survive conditions that would instantly crush a normal building? How do they protect billions of dollars of cargo and, more importantly, the lives of the crew on board? The answer is an incredible mix of engineering, physics, high-tech weather forecasting, and old-school maritime grit. To understand how a ship survives a storm, you have to discard the idea that it's just a bigger version of a recreational boat. A modern container ship or bulk carrier is a masterpiece of heavy industrial design, engineered from day one to be an impenetrable fortress. The outer skin of a cargo ship, known as the hull, is not just sheet metal. In critical areas, such as the bow, which takes the direct pounding of the waves, and the keel, which is the bottom spine of the ship, the steel plating can be several inches thick. This isn't ordinary steel either. It's high-tensile, specialized marine-grade steel designed to resist both the corrosive attack of salt water and the extreme structural fatigue of constant impact. If a ship were just a hollow steel shell, the first major wave would cave it in like an empty soda can. Inside the hull lies a massive, intricate skeleton of longitudinal frames running the entire length of the ship to prevent it from buckling, transverse webs that maintain the cross-sectional shape against the crushing pressure of the deep ocean, and heavy steel walls called bulkheads that divide the ship internally. One of the greatest innovations in shipbuilding history is the concept of watertight compartmentalization. The interior of a cargo ship is not one giant open room. Instead, it is divided into dozens of isolated, self-contained chambers. If a rogue wave or a piece of floating debris punches a hole through the outer hull, the water cannot flood the entire ship. It fills that single compartment, hits a massive, heavily reinforced bulkhead door, and stops. The ship will sit slightly lower in the water, and its balance might change, but it will not sink. In the middle of an ocean storm, damage control isn't always about stopping water from getting in. It's about controlling exactly where that water is allowed to stay. When people think of strength, they usually think of absolute stiffness, like a diamond or a massive concrete bunker. But in ocean engineering, absolute stiffness is a death sentence. If a 1,200-foot-long ship were perfectly rigid, the sheer physics of the ocean would snap it in half within its first year of service. When a ship crosses a massive storm, it encounters two primary structural nightmares known as hogging and sagging. Hogging occurs when a ship crests a massive wave. The peak of the wave is directly under the center of the ship, supporting it, while the bow and the stern are hanging over the empty valleys on either side. Gravity pulls the ends down, causing the middle of the ship to arch upward like a cat's back. Sagging is the exact opposite. The bow and stern are supported by two separate wave crests, while the middle of the ship is suspended over the empty trough between them. The weight of the cargo pushes the center of the ship downward. During a severe storm, a ship will alternate between hogging and sagging thousands of times. To survive this, engineers design ships to flex. Think of a tall skyscraper in a major city. During a hurricane or an earthquake, those buildings don't stand perfectly still. They sway back and forth by several feet to prevent the structural stress from building up and shattering the base. On a giant container ship, if you stand in the central superstructure and look down the long corridor that runs the length of the ship beneath the deck, you can actually watch the steel frame twist, bend, and curve. The bow might rise or twist up to several feet relative to the stern. By allowing the ship to behave like a giant, ultra-stiff spring, the energy of the waves is absorbed and distributed throughout the entire structure rather than breaking a single point. A watertight, flexible ship is a great start, but it doesn't mean much if the ship turns upside down. This brings us to the ultimate hidden danger of ocean transport, which is the cargo itself. A modern, ultra-large container ship can carry over 24,000 standard shipping containers, and many of these containers weigh upwards of 30 tons. When you stack them 20 high above the deck, you are dealing with hundreds of thousands of tons of dead weight suspended high above the water. If that cargo shifts even a few inches during a storm, the kinetic energy generated can instantly destabilize the ship, leading to a catastrophic roll. To keep a ship upright, marine architects must master the relationship between the center of gravity and the center of buoyancy. The center of gravity is the point where the total weight of the ship and its cargo is concentrated, while the center of buoyancy is the geometric center of the underwater portion of the hull, which is essentially where the ocean is pushing back up against the ship. When a ship rolls to one side because of a wave, the shape of the underwater hull changes, shifting the center of buoyancy to that same side. This creates a distance between the upward push of buoyancy and the downward pull of gravity, forming an invisible lever called a righting arm that pulls the ship back to an upright position. The distance between the center of gravity and the ship's stability point determines how the ship behaves. If a ship is loaded with too much heavy cargo at the very bottom, it becomes what mariners call a stiff ship. It will snap back upright incredibly fast and violently, which risks snapping the steel container connections and injuring the crew. If the heavy cargo is loaded too high, it becomes a tender ship, rolling deeply and taking a long time to recover, which risks capsizing the vessel. To achieve the perfect balance, loading a ship is never left to guesswork. Weeks before a ship arrives at a port, sophisticated stowage planning software maps out the exact location for every single container, placing the heaviest items deep in the belly of the ship and lighter items on top. Once the containers are perfectly distributed, they must be physically anchored to the ship. This is a brutal manual job done by port workers and the crew using 3 layers of defense. First are twist locks, which lock the corner castings of every container into the one below it with a heavy steel deadbolt, turning a stack of 10 containers into a single, unified tower. Next are lashing rods, which are long, heavy solid steel bars that run diagonally to form a massive X-bracing system. Finally, heavy-duty screw devices called turnbuckles are used to crank the lashing rods down to immense tensions, eliminating any microscopic slack. When a storm hits, the ocean doesn't just push a ship left and right. The sea attacks a vessel in 6 distinct axes of motion simultaneously. There are 3 linear movements where the ship moves bodily along an axis. Heave, where the entire ship is lifted vertically upward by a rising swell and dropped into a trough. Sway, where the ship is pushed bodily sideways by wind or currents. And surge, where the ship is accelerated forward or slowed down backward as waves pass beneath the hull. Then there are 3 rotational movements. Roll, where the ship tilts from side to side. Pitch, where the bow rises high into the air and plunges downward. And yaw, where the bow swings left and right off its intended course. Among all these motions, there is one phantom threat that captains fear above almost all else, known as parametric rolling. This doesn't happen when a ship is hit from the side by waves. Remarkably, it happens when a ship is sailing directly into or directly away from them. If the length of the ocean waves matches the exact length of the ship and the timing of the waves aligns with the ship's natural rolling frequency, the ship's stability fluctuates wildly as it pitches. Within just a few wave cycles, a gentle 2-degree roll can amplify exponentially into a violent 40-degree tilt. The ship begins rolling from side to side like a pendulum gone mad, which can tear apart the steel lashing systems and dump thousands of containers into the ocean. Surviving a storm is easier if you are never in it in the first place, and modern maritime strategy relies heavily on avoiding the worst of nature's wrath through technology. Long before a cargo ship faces a 50-foot wave, a team of shore-based meteorologists, routing engineers, and the ship's officers are tracking the weather using a global network. They utilize dynamic weather routing software that takes real-time inputs from geostationary and polar satellites, wave radar satellites measuring the exact height of ocean swells, and oceanic buoys reporting local wind speeds and atmospheric pressures. The software runs complex algorithms to simulate thousands of different route variations, calculating the ship's fuel consumption, engine load, and structural stress for each option. A captain will gladly add hundreds of miles and tens of thousands of dollars in fuel costs to circle around a severe low-pressure system. Avoiding a storm is always cheaper than fighting one because the damage to the ship, the potential loss of cargo, and the massive delays caused by crawling through rough seas are far more expensive than taking the long way around. Sometimes, despite all the planning, a storm shifts faster than predicted, or a ship finds itself on a route where there simply is nowhere to hide. When a ship is caught, driving a 200,000-ton vessel through a hurricane becomes an art form that requires decades of experience. A common mistake people make is assuming that a ship should face a massive wave completely head-on. It seems logical to let the sharp bow cut through the water like a knife. In reality, slamming straight into a 50-foot wall of water at full speed is disastrous. The wave will strike the flat underside of the bow with hundreds of thousands of tons of instantaneous force, creating a vibration that travels down the entire steel spine of the ship like a tuning fork, which can fracture welds or throw equipment offline. Taking a wave directly from the side is even worse, as it leaves the ship vulnerable to being rolled past its point of recovery. Instead, captains position the ship so that the waves strike the bow at a 20 to 45 degree angle, known as a bow quartering C. This allows the ship to gently ride up and over the shoulder of the wave, distributing the lift across a wider area of the hull and preventing violent structural slams. When conditions get truly extreme, the natural human instinct might be to stop the engine, hunker down, and wait for it to pass. In shipping, that is a fatal mistake. A ship needs water flowing past its rudder to steer, a capability known as steerage way. If a ship loses its engine power or slows down too much in a storm, it loses the ability to steer. The wind and waves will instantly catch the massive profile of the vessel and turn it sideways into the troughs of the waves. Once a ship is broadside to a hurricane-force sea without power, its chances of survival drop drastically. The captain must maintain a delicate balance, keeping the ship fast enough to retain steering control but slow enough that it doesn't slam into the next wave with destructive kinetic energy. While we marvel at the steel, the algorithms, and the physics, we must not forget the human beings living inside this mechanical world. A typical modern cargo ship crosses the ocean with a remarkably small crew, often just 20 to 25 people, including the captain, officers, engineers, and deckhands. When a major storm strikes, the ship's superstructure, which is the accommodation tower where the crew lives and works, becomes a chaotic environment. The bridge of a container ship is located high up in this tower, often 100 feet or more above the waterline. Because of basic geometry, when the bottom of the ship rolls by just 10 degrees, the bridge at the top of the tower moves sideways through a massive arc of 30 or 40 feet. Standing on the bridge during a storm doesn't feel like a smooth roll. It feels like being thrown back and forth across a room. When the weather gets rough, life on board transitions into absolute lockdown mode. Every chair, computer, pot, pan, and tool is physically chained, bolted, or strapped down because loose items become lethal projectiles when a ship rolls violently. Storm ropes are strung along corridors so crew members can pull themselves along without being thrown into walls. Sleeping becomes nearly impossible, and crew members must wedge themselves into their bunks using specialized storm boards or rolls of blankets to avoid being thrown onto the floor. Cooking a hot meal in a galley that is tilting 30 degrees is out of the question, so the crew subsists on simple, cold rations that can be eaten with one hand while the other hand holds onto a secure railing. Despite the fear, the exhaustion, and the physical toll, the crew carries out constant inspections. Engineers descend into the loud, hot-moving depths of the engine room to ensure the main power plant never falters, while officers stay glued to the radar screens and windows on the bridge, guiding their steel home through the dark. The next time you look at a global map and see the vast blue emptiness of the oceans, remember what is actually happening out there right now. Dozens of ships carrying everything from life-saving medical supplies to the components of your next device are actively dancing with the absolute worst conditions nature can conjure. They survive not because they are stronger than the ocean, but because they respect it. They survive because their flexible steel hulls absorb forces that would shatter rigid structures. Their watertight compartments isolate damage. Their meticulously calculated cargo placement ensures they always want to stay upright. Their global satellite networks allow them to outsmart weather systems, and their highly trained crews possess the calm judgment required to pilot a skyscraper through a liquid mountain range. It is a silent, almost invisible triumph of engineering that keeps our modern world connected, proving that humanity's floating giants are truly some of the toughest machines ever built.